Now we need to find a mathematical framework for quantum mechanics. So the basic idea, again, as I said, basic postulate is the principle of superposition. Now we can look at mathematics, some mathematics textbook or mathematics that we have studied. Are there mathematical objects that obey the principle of superposition? All right, and if you are already familiar with these things, maybe the word vectors come to your mind. Why? Because vectors behave like this, right? The principle of superposition is actually fundamental to vectors, right? If you have two vectors, a vector and b vector, all right, then a vector plus b vector is also another vector in the same space. If you take the three-dimensional space, etc., okay, if you take the three-dimensional space, you have got a vector and b vector, and you get another vector which is also in the same space, which is also in the same space. Okay, so you see that the vectors obey the principle of superposition in a sense. Maybe we can represent a quantum mechanical state by vectors, and then you will be able to incorporate this principle of superposition. All right, this is almost true. If you have thought of vectors already, this is almost true, but we need a generalization. All right, because the three-dimensional vector space, the real vector space, is not sufficient. Because in the real vector space there are only three independent directions. But we know that if you are talking about electron being at different places at the same time, if you take space, there are an infinite number of independent positions, right? It could be here, it could be there, it could be there. All right, so three-dimensional vector space is not sufficient, right? We need something more. So, and if you look at some mathematical textbooks, or if you look at your mathematical physics textbook, somewhere you'll see that there is a mathematical formalism called linear vector space. Okay, this is a generalization of vectors. Linear vector space is a generalization of vectors. Linear vector space is a generalization of ordinary vector space. There are two directions in which you can make the generalization. We allow the scalars to be complex numbers. All right, we know that vectors can be, for example, if we know that vectors can be written as A is equal to a vector. Let's say like a vector is equal to axi plus ayj plus azk. Here this ax, ay, az are numbers. These are real numbers. Okay, and this I, J, K are directions, right? So these are real numbers. And we make, in our generalization, we allow these numbers to be complex. Also, we do not restrict ourselves to three dimensions. We cannot restrict ourselves to three dimensions because in three dimensions we have only three independent directions. But when you talk about positions, for example, there are an infinite number of independent positions in space. Each position is independent from the other. All right. So it could be infinite dimensions. So we cannot restrict ourselves to three dimensions. Now, what we need to understand is that the formalism of linear vector space existed even before quantum mechanics. Even before quantum mechanics was invented, the formalism of linear vector space was well developed in mathematics. So if you are a mathematical student and if you are a mathematics student and if you have heard about linear vector space, maybe we'll be able to make this identification. The principle of superposition, okay, this looks a lot like linear vector space. All right, this is a thing that we could try. This is something that we could try to construct a mathematical framework. All right. And this is a good guess. Okay, now let's look at what we mean by vector space. A vector space consists of a set of vectors. The space consists of a set of vectors together with a set of scalars, which is closed under two operations: vector addition and scalar multiplication. What does this mean? This means that if you add two vectors in a space, you get another vector. That's all. Right? In this case, we'll describe the vectors like this, okay, with an angled bracket. So a vector space consists of a set of vectors together with a set of scalars, which is closed under two operations: vector addition and scalar multiplication, which means that if you add two vectors, you'll get a vector in the same space. If you multiply the vector by a scalar, you'll get another vector in the same space. It does not take it out of the space. So vector addition and scalar multiplication do not take these things out of the vector space. Okay, and here the scalars are ordinary complex numbers. What do we mean by closed? This means that the above mentioned operations will never carry you out of the space. If you define the space as a set of vectors, all right, these these operations, okay, vector addition and scalar multiplication, will give you a vector in the same set. It won't take you out of the set. Okay. So the sum of two vectors is another vector. Now the vectors are denoted by some symbol in an angled bracket. Okay, we'll denote. So since we are going to linear vector space, I think this notation is not sufficient. We'll invent a new notation. This is known as the Dirac notation, an ingenious notation. All right. So we'll represent vectors using this thing. All right. Instead of doing this thing, we'll represent it using an angled bracket. Vectors are denoted by some symbol in an angled bracket. For example, like alpha in an angled bracket, or an up arrow in an angled bracket. Okay. So what we do is that we put in the available information that represents the state inside this angled bracket. Okay. These are vectors basically. So we represent vectors by this notation. Okay. Now the closure under addition, the first thing, vector addition, we said that the space is closed under addition. The closure under addition is simply stated like this. If you have two vectors alpha and beta and you add them, you get another vector in the same space. Okay. The property of closure under addition and multiplication by scalar lets us construct vectors which are a linear combination of other vectors. All right. So if you have alpha, beta, gamma, etc. as vectors, you could construct linear combinations of these vectors by adding them. After multiplying with scalars, you will get another vector in the same space. That is, if alpha and beta are, we call this as ket. Okay, we'll call this as ket. Okay, the reason for naming it like that will be explained later on. Okay, we'll see that later. Doesn't matter. We'll just imagine of it as the name of this kind of objects. We'll call it as ket. Okay, so ket alpha and ket beta are vectors in the linear vector space. Then a ket alpha plus b ket beta is also a vector in the linear vector space. All right. Now this is nice. Okay, look at this statement. We are saying that if alpha and beta are vectors in the linear vector space, then so is a alpha plus b beta. Okay. Just before we said that if S1 and S2 are possible states in which the electron can be, then S1 plus S2 is also a possible state of the electron. Right? This was the principle of superposition. So comparing this property with the principle of superposition leads us to the following identification. Quantum mechanical states can be represented by vectors in linear vector space. Okay. Now, this is not a logical proof for this statement. There was no logical proof for this state. Okay. So the idea is that we looked at the double slit experiment and we saw that the electron obeys some kind of superposition principle. And then we looked at the mathematical textbooks and we saw that there was something called this linear vector space, and the behavior, the mathematical objects in the linear vector space seems to behave similarly as the electron. So we try this identification, right? We make a guess and we said, okay, why don't we represent electrons by vectors in linear vector space? Okay, because we can incorporate the principle of superposition in a simple manner, right? So the state space of the quantum mechanical states can be represented by vectors in linear vector space. Now, generally, the state space of quantum mechanics is called the Hilbert space. So it's actually a linear vector space with inner product, etc. We'll come to that. Right? So now, for the moment, you just add this to your vocabulary. Okay. In classical mechanics, the state space was called phase space. In quantum mechanics, the state space is called Hilbert space. Okay. So in the mathematical formulation, vectors in linear vector space corresponds to possible states of the system. Okay, why did we make this identification? Because of the principle of superposition that we saw in the double slit experiment. Okay, this identification lets us incorporate the principle of superposition in a beautiful and simple way. Okay, so we chose linear vector space to incorporate the principle of superposition. Okay, all right. Now, again, as I said, all right, the reason why we continue with this mathematical formalism is that it works. Okay? There are two things it should satisfy. It should describe the physical system, The mathematical framework should be logically consistent and it has to make the correct predictions. Okay, if these three conditions are satisfied, then we say that okay, this mathematical framework is correct, or this mathematical formalism seems to describe nature correctly. All right, if not, we have to discard it. Yeah, but this is something that works. Ultimately, the justification for this mathematical framework is that it actually works. It actually succeeds in making measurable predictions which are very accurate. All right? That's why we believe that this is the correct mathematical formalism, or at least this is one correct mathematical formalism of quantum mechanics, or the microscopic behavior. Okay. All right, now we have identified states of quantum mechanical systems. What about observable quantities? All right, we said that states can be represented by vectors in linear vector space. Okay, how do you extract the measurable quantities from that? All right, so we can maybe make a guess. Okay, so again, before going into this linear vector space, if you are familiar already with matrix algebra, linear algebra, etc., then you are already familiar with the logic of linear vector space. Okay, you have already studied the logic, the basic logic of linear vector spaces. All right, because we'll see that these matrices, for example, column matrices are examples for vectors in linear vector space, or we can say that column matrices actually make a linear vector space. Okay, and if you're familiar with linear algebra or matrix, what do you say, matrix algebra, etc., then you are already familiar with the logic of linear vector space. So this is going to be easy, all right? Mathematically, quantum mechanics is going to be easier than classical mechanics. It's just linear algebra, right? Okay. Now again, how do we extract the what do you say? How do you extract information about observable quantities, measurable quantities from the state? Now we have to look for some other object. Okay, as I said, if there are two possible states, okay, slit 1 and slit 2, then it could be measured either in slit 1 or slit 2. If there are three possible measurements, measurement result, like let's say slit 1, slit 2 and slit 3, then you would have three possible measurement results. Okay, and if there are four, there would be four possible measurement results, etc. Okay. Now you see that instead of so when you try to represent an observable quantity, it cannot be a single number or something. It should be some sort of a collection of numbers. It should be some sort of a collection of numbers. All right. Now, if I already made this identification with vectors, and if you think of collection of numbers, the first thing that should come to your mind is matrices, right? Matrices are collection of numbers. So maybe we can represent measurable quantities by square matrices, or generally by operators. All right, we call this as square matrices are actually examples for operators. Why do we say that? Because if you have a column matrix and a square matrix acts on it, you get another column matrix. Okay, you can talk about it like this: B is a square matrix, C is a column matrix, and B acting on C gives you another column matrix. So this B can be called an operator. What do we mean by operator? Operator is something that acts on a column matrix and changes it to another column matrix, right? This is just an example, right? There are other operators that we'll look at. So operator, so we can make a definition of operator. An operator defines a relation between two vectors, just like a square matrix defines a relation between two column matrices. Okay, you can say that square matrix defines a relation between two column matrices. Okay, so you could make it general. In general, an operator defines a relation between two vectors. So if you have two vectors alpha and beta, there's an if you have an object that relates them, then this is called an operator. And as I said before, we started with an example. A square matrix acting on a column vector is an example. Okay, a differential operator acting on a function is also an example. Right? If you have a differential operator, d by dx of, let's say, x square, okay, this would give you 2x. So this d by dx can be called an operator that acts on this function and changes it into another function. Okay. All right, so we make this guess that square matrices are more generally operators. Okay, so we already identified states with states with vectors. So now we make the identification that maybe operators associated with this vector space has something to do with measurable quantities. Okay, so we try this thing. Observables in quantum mechanics are represented by operators that act on state vectors. All right. The good thing is that when you study linear algebra, once you make the identification that states are represented by vectors, there are not many other things that we can choose from. Right. So if you already choose states, if you already choose vectors to represent states, and then you have something else to represent observable quantities. All right. So there are not many options that we can look for, and a good option is that it's operator. Measurable quantities can be represented by operators. Okay. Now, what about measured values? We said that there could be a number of measured values, and we know that measured values are always real numbers. All right. First, let's think about it like this. Okay, we said that measurable, all right, observable quantities can be represented by operators. For example, square matrix. Okay, square matrix is an example for an operator. Okay, so let's say that we are representing an observable by a square matrix. Now we need to extract the possible measured values from this square matrix. All right, so we are looking at some numbers associated with this matrix, which somehow characterize this matrix. Okay. Now, what are the basic numbers that characterize the matrix? Okay. When I say characterize the matrix, we are looking for numbers. We need to look for numbers which do not change under a similarity transformation, etc. And one obvious choice might occur to you. These are the eigenvalues. So matrices square matrices can be diagonalized, okay, and then you will get the eigenvalues of the matrix. Eigenvalues will give you like lambda 1, lambda 2, lambda 3. These are a set of numbers which do not change under a similarity transformation, and these are somehow numbers that characterize the essence of a matrix. Okay, so if you want to associate some numbers with the matrix, a good choice is the eigenvalues. All right, a good choice is the eigenvalues. So maybe we can say that the measured values, no, we are saying that the measured values are associated. Okay, because we already made the identification that observables are operators, for example, matrices. So we make the association that measured values are eigenvalues. Okay, measured values are eigenvalues. We know that eigenvalues are important. You have studied how to calculate eigenvalues, how to find the eigenvalues, etc. So let's do something. Let's make use of that. Let's say that measured values are associated with eigenvalues. There's a small problem there. Eigenvalues for a matrix, okay, it could be real or complex, but measured values are always real numbers. Measured values are always real numbers. Okay, so we need to look for so the measured values are only eigenvalues. This means that we need to look for operators. We need to look for operators whose eigenvalues are always real. Whose eigenvalues are always real. All right, and there is a class of operators like that. These are called Hermitian operators. Hermitian operators. You might have studied Hermitian matrices. Okay, it's the same logic. For a Hermitian matrix, the eigenvalues are always real. Okay, so we have to make a small modification to our earlier identification. We said that observables can be represented by operators. Now we say that observables can be represented only by Hermitian operators. Okay, operators whose eigenvalues are real. Okay, this is what we are coming to. So in the logic, in the language of linear vector space, this is what we mean by an eigenvalue equation. When an operator acts on a state, you get the same state multiplied by a number. Okay, then we say that this is an eigenvalue equation. We say that ket alpha is an eigenvector of operator m corresponding to the eigenvalue alpha. Okay, now you should not be confused by using alpha here and here. Okay, this is a number. This alpha here is a number. All right, the eigenvalue, and this ket alpha is a vector. These are different objects. Okay, here we are only choosing to represent a vector by the corresponding eigenvalue of an operator. So here we are simply representing a vector by putting the eigenvalue inside a ket. This is a kind of representation that we will be using throughout our course. Okay, we'll represent vectors by putting the eigenvalues inside a ket. Okay. So ket alpha is called the eigenvector of M corresponding to the eigenvalue alpha. Examples can be found for matrix operators, differential operators, etc. Okay. So we make the association that measured values are eigenvalues, but eigenvalues can be real or complex. Measured values of observables are always real numbers, all right? So if you measure the energy, the momentum, position, etc., right? Uh, you might have carried out experiments in the laboratory. There are readings, you can in the voltmeter or anything, all right? All these things, voltmeter or ammeter, all these things are always real numbers. Okay, we never measure complex numbers. Okay, so all operators cannot observables, but only those with real eigenvalues. Okay, so once we associate measured values with eigenvalues, this means that we cannot choose all operators to represent observables. We can choose only those operators with real eigenvalues. An observable must be represented by only those operators whose eigenvalues are real. There is a class of operators like that. These are called Hermitian operators. And we already have an understanding about what Hermitian matrices are, but we'll be explaining what this thing actually means, how to define a Hermitian operator, etc. These things we'll be discussing. All right. At the moment, we are only having an overview of the kind of things that we are going to learn. So here basically we have identified a correspondence between nature and mathematics. Quantum mechanical state in nature, this is nature here. In nature, there are something called as quantum mechanical state, and in mathematics, there are vectors in linear vector space or Hilbert space. Okay, so quantum mechanical states will be represented by vectors in Hilbert space. Quantum mechanical observables will be represented by Hermitian operators, and measured values will be associated with eigenvalues of Hermitian operators. Okay. We said one more thing. We said that we should be able to predict the probabilities of measurement, and we will be able to predict probabilities of measurement from this. But for that, we need to do a little bit more work. Okay, we'll be doing that later on. But you remember that there is one more thing missing here. We need to be able to make predictions. Okay, one kind of prediction we can already make from this mathematical formalism. Once we find these things, you can ask the following question: what are the possible measured values for an operator represented by a given operator? Okay, if you have a matrix, for example, square matrix, which represents an observable, you can be asked what are the possible measured values. This you can find using your existing mathematical skill. You just find the eigenvalues. You just find the eigenvalues of the operators, and these would be the possible measurement outcomes. We also need to be able to predict the probabilities for each of these outcomes. We'll see how to do this in the following classes. Okay. Now you see that there is a similarity with classical mechanics. In classical mechanics also we have called states. For example, states are represented by position and momentum. Okay, there's also time evolution of the state. Once we have the state at any time, you can find the state at any other time by solving Newton's equation. For example, F equal to dp by dt, where P is equal to m dx by dt. All right, or equivalently, you can find the evolution of the state by solving the Hamilton's equations of motion. All right, the basic idea is that we have got equations of motion in classical mechanics. What do the equations of motion do? They give you the state of the system at any time. If you have the information at some other time. All right. So if you know the state at any time, you can find the state at any other time using these equations of evolution. All right. Examples are Newton's equation or Hamilton's equation. All right. I think a better example is Hamilton's equations in this context, because Hamilton's equation actually says that the Hamiltonian, there's something called the Hamiltonian that governs the time evolution of the system. Right. In this context, you need to find the Hamiltonian to find the time evolution of the system. All right, you already know the Hamilton's equations, and I think x dot is equal to derivative with respect to p, and p dot goes like this. Okay, there's a minus sign here. I think this is correct. Okay, so you see that the Hamiltonian actually governs the time evolution of the system. And similarly, in quantum mechanics also we have states. States are vectors in linear vector space. There is also an evolution equation. which is the Schrodinger equation. All right, these equations, okay, these are fundamental. We don't basic this Newton's equation, etc. These are fundamental. All right, we identify that this is the kind of equation by which a system evolves. Okay, in quantum mechanics also we have an evolution equation. It's called the Schrodinger equation, and in the Schrodinger equation also there is a Hamiltonian appearing. This is called a Hamiltonian operator. Again, the time evolution is governed. You see that the time evolution is governed by the Hamiltonian operator. And this H cross here, H bar, we call this as H bar. H bar here actually say something. It comes from the Planck's constant, and it says that we are dealing with quantum mechanics. There is something interesting here. There is an I here, and we know that I is associated with complex numbers. It's called imaginary. I is equal to square root of -1. So this also says that complex numbers are going to be very important in quantum mechanics. These are fundamentally important. In classical mechanics, complex numbers were used to make some of the calculations easier. In quantum mechanics, these appear in a more fundamental manner. Now, in quantum mechanics, there's another problem called the interpretation problem. The question is, what is the reality that's described by quantum mechanics? Okay, what does quantum mechanics actually mean? All right, we know that quantum mechanics is a mathematical framework. We know how to make predictions, etc. But the question is, what does it actually mean? In classical mechanics, we have never encountered an interpretational problem because it's very clear what classical mechanics what this represents, what classical mechanics uh, describes. Okay, classical mechanics basically describes the macroscopic world. It's the world that we experience. So there's no question as to what kind of reality classical mechanics describes. In quantum mechanics, things are different. All right, there are so many weird things happening, which is completely out of our experience. All right, it's completely different from the world that we experience. The quantum mechanical world behaves in such a way that is completely out of our experience. All right, we cannot even imagine what's going on there. We cannot form a mental picture. It's not possible to form a mental picture of how quantum mechanical world actually behaves. This is the reason why we have interpretations of quantum mechanics. Okay, interpretations deal with the questions like, what does superposition actually mean? Right? Can electrons actually be in two different places at the same time? The mathematics seems to suggest that electrons can be at two different places at the same time, but can it be? And then there's another question, what happens in a measurement? We said that the electron can be in two slits at the same time. When you make a measurement, it is always found in either slit. And then you can ask what happens during a measurement. All right, so these questions are what form the interpretation problem in quantum mechanics. So there are basically two types of interpretations. Okay, we won't be studying this interpretation in detail. This is the only place where I will mention this. Okay, so there are basically two types of interpretation. One type of interpretation takes the mathematics literally. Okay, take the mathematics literally. Okay, this says that okay, the quantum mechanics is very good at making predictions, and it's always the predictions of quantum mechanics always have turned out to be correct. So this means that there is some truth to this mathematics. So we take the mathematics literally. So when you take the mathematics literally, if I write a state like this, okay, this would mean that the electron is actually in both slits at the same time. The electron can be at different places at the same time. So if you take the mathematics of quantum mechanics literally, that would mean that an electron can actually be at different places at the same time. Okay, there are other interpretations which say that you cannot take this mathematics seriously. Okay, the mathematics of quantum mechanics is just a set of rules to make predictions. It does not describe the actual thing that an electron does. The mathematics of quantum mechanics does not actually tell us what an electron does when we are not looking. Okay, the mathematics of quantum mechanics is only a set of tools. It's only a mathematical tool in order to make predictions as to what the outcomes of measurements are. All right, so they say the other type of interpretation says that it's only a mathematical tool. It's only a mathematical tool. It does not tell us about what an electron, for example, does when we are not looking. Okay, so I'll just coin a few words here. An example for the first kind of interpretation is called the many worlds interpretation. Okay, it's a very interesting interpretation and probably the correct interpretation. And the example for this kind of interpretation, where we don't take the mathematical framework literally, okay, this is one example, is the Copenhagen interpretation. There are many interpretations of quantum mechanics. I have just included only two of the most prominent interpretations. Okay. Now, throughout the course, I will be assuming that the mathematics of quantum mechanics literally describes nature. Okay, so I'll assume that. So I will be going with the first type of interpretation, where the mathematics is taken literally and nature is actually exactly represented by the mathematics of quantum mechanics. Okay, so this will be the interpretation that I will have in the back of my mind when I talk about these things. All right, because writing a mathematical statement is one thing and talking about in a language is another thing. In quantum mechanics, whenever you talk about an equation, somehow some sort of interpretation should appear. All right, and I will make it precise here. The interpretation that I will have in my mind when I use sentences in English, when I try to explain these mathematical equations, will be that the interpretation that we will use, I will use in the course, is that the mathematics of quantum mechanics literally describes nature. Okay, this is the reason why I said that an electron can be at different places at the same time. It's in this type of interpretation that we say that an electron can be at different places at the same time. And I believe that this is the right way to look at the mathematics, but not everyone agrees. Okay, people have different opinions about this. You can read all about these things. I'll also give you some fun things to read. You can read about the Schrodinger's cat, and you can read about Copenhagen and many worlds interpretation. Okay, so I leave this as extra reading. You can just make a Google search, etc., and you can read about these things. And this Copenhagen interpretation, there's another way to talk about Copenhagen interpretation. It's basically uh, called shut up and calculate. Shut up and calculate. Okay, so the basic idea of Copenhagen interpretation is that quantum mechanics is a set of rules that we have to calculate probabilities. Okay, you know the rules, so shut up and calculate. Don't ask about what it means about nature, etc. It's a useless question. Okay, this is the basic idea of Copenhagen interpretation. And for most of the course, we'll be developing the mathematical framework, and mostly what we'll be doing is to shut up and calculate. Okay, this is what we'll do throughout the course. And in your leisure time, maybe you can read about these interpretations, etc. But better not waste too much time on it. Better shut up and calculate. Okay. So with that, I'll conclude this session. Basically, what we have done is that we have looked at one thought experiment in order to understand how the quantum mechanical world actually behaves. The thought experiment was the double slit experiment. From the double slit experiment, we came to this idea called the principle of superposition. All right, we looked for mathematical objects that behaves like electrons, and we saw that vectors are a good choice. And immediately we realized that vectors in three-dimensional space or real vector space cannot work. Then we look at some mathematical textbooks and we see that there is something called linear vector space. We can use linear vector space to represent, to incorporate the principle of superposition. So we say that we can identify states of the, so we basically looked for correspondence between nature on the one hand and mathematics on the other. Mathematics. Okay. In nature, we have got quantum mechanical states. In mathematics, this will be represented by vectors in linear vector space. Okay. And then we have got observable quantities, because this is something that we can actually measure. Observable quantities. Observable. This will be represented by operators. So we have got vectors and operators. And we said that these are not all operators can be used to represent an observable. We'll use only the Hermitian operators. Why Hermitian operators? Because Hermitian operators have eigenvalues which are always real. And we made the identification that measured values are some values that are associated with observables or associated with operators, and a good identification was the eigenvalues. Okay. Later on, we'll see that the reason why we believe in this kind of thing is that we can make correct predictions. Okay. All right. With that, I'll conclude this session and we'll continue in the next class. Thank you.